what's interesting about most of the transition metals is that they do not form a single stable ion the same way that nonmetals do or 1a and 2a do. Okay? 1a always formed a plus charge, 2a always forms a 2 plus charge, aluminum, gallium always 3 plus. Okay? Transition metals do not just have a single one that they form. They can form 2 plus or 3 plus or something. They can form multiple different stable ions. So, for instance, iron. The iron cation in different compounds is sometimes 2 plus, and other compounds it's sometimes 3 plus. Okay? So, you can understand how something like iron chloride would be an incomplete name, because names of ionic compounds describe the ions. If we just say iron, we're not sure which of the possible iron cations we're talking about. Okay? That's unclear on whether it is Fe2 plus or Fe3 plus. Okay? However, if you're given a chemical formula, you can figure out which particular ion we're using. Okay? Look at FeCl3. This is a 1:3 ratio of iron cations to Cl. And chloride is always Cl minus. Okay? That does not change. So if we know we have a 1:3 ratio of whatever iron is to those Cl minuses, okay? In other words, I have 3 of these Cl minuses for every 1 of those irons, okay? That means this must be Fe3 plus. Okay? And likewise, this one with the 1:2 ratio must be Fe2 plus and Cl minus. Okay? You can tell from that. So what we're going to do, instead of just calling them iron chloride, because that's not enough information, for the name of this one, we're going to call it iron, and I'm going to put a Roman numeral 3 in parentheses right after iron. Okay. This one, iron 2 chloride. Okay? Because remember, when we're naming an ionic compound, we're naming the positive ion and the negative ion. Okay? The iron 2, okay, that literally means it's an Fe with a 2 plus charge, because that's chloride. Iron 3, Fe3 plus charge, chloride. Okay? That extra Roman numeral that we've used in parentheses there indicates what? What does that 2 stand for? It indicates the positive charge on the variable charge metal cation. For a transition metal or some other metal that has multiple different charges that it can make, we use that Roman numeral to indicate which particular plus charge we had. Okay? So, let's give that a try. Now, it's very important when you're given a name like this to understand that those are the names of the 2 different ions. In a lot of cases, that's not going to look very much like the formula. Okay? Let's see if we can figure that out. Titanium 4 chloride. Titanium is Ti. Ti is a transition metal here that does not have one particular fixed charge. We're going to have to figure it out. Okay? But the nice thing about being given a name is that here we have the Roman numeral that tells you what the charge is. IV is 4, and since it's a metal, it's 4 plus. Okay. Chloride is just always minus. Okay. Those are the ions. That's the ion pair. Okay. So whenever you're given a name, that's pretty easy. the Roman numeral automatically tells you what the plus charge is, so you just need to fill that in. Okay? And then remember what we do to figure out how many of those we need? What do you do to those numbers? You just switch them. It is a 1 to 4 ratio. For every 1 titanium 4 plus ion, we'll need 4 of these chloride ions. Okay? So the ratio just tells you the formula. Remember, the name tells you the ion pair. You have to switch then to make the ratio. Okay? So you might be thinking, okay, I got a 4 there, I got a 4 there. That's not so bad. Well, be a little bit careful, because look at what happens in this one. Titanium 4 oxide. Titanium, its charge in this case is again 4 plus, but it's not because that's always what it is. It's because that's what this Roman numeral says. There are titanium 2 compounds, and titanium 6, and titanium 3. Titanium has a lot of them. Okay? And you don't need to know what all of them are. All you need to know is here we've got titanium 4. That means we've got Ti with a 4 plus charge. Okay? The difference here is that oxide is 2 minus. Okay? So, 4 plus and 2 minus. You can start to think of how those fit together, or you could just switch them. If you switched them, you'd have 2 to 4, but that's not a simplified ratio. The simplified ratio would be 1 to 2. Or you could also think of it like if I had one of those titanium 4 plus ions, then how many of these oxide ions do I need to make it neutral? Well, I need 2 of them. I need that one and I need that one. And then you should be able to see that that's a neutral grouping of atoms. But if we decide that for every 1 titanium we need 2 of these oxides, we should be able to write the formula. It's TiO2. See where that comes from? It's very important. Titanium 4 oxide doesn't even have a 4 in the formula. That's why it's so important to think about the plus charge and the minus charge of each of those ions. That's absolutely critical in order to get that right. Okay? So I'm going to go the other direction for you here. Remember, if you start with a formula, that's exactly the same as the ratio. Then all we need to do is figure out what the charges are, and that becomes the name. Okay? So ratio is easy. That's just straight from the formula. 1 to 6, 1 to 2, 2 to 3. Okay? Formula and ratio say exactly the same thing. That's very important. Okay? Now what we're going to do is figure out the ion pair. Tungsten, again, is a transition metal. It's right here, so I don't know what its charge is right away anyway. I'm going to leave it blank. F, we do know what F's charge is. Straight from the periodic table. F has a minus charge when it's in an ion, so we can write that. Okay? So now, what I'm going to do, I'm going to say I have F minus, okay? I have 6 of them. All right, there's 6 in the ratio. That makes 6 minus charges in the formula. Okay? I only have 1 tungsten in the formula. That 1 tungsten is going to have to take over all of the plus charge in order to balance that out. Okay? So I have 1 tungsten, right, in the ratio, which means that that tungsten is going to have to be 6 plus. Okay? So the name will come straight from that. It's going to be tungsten. And then because tungsten is not fixed charge, tungsten is variable charge, we have to write what its charge was. And 6 is Vi. Tungsten 6. Chloride. Okay? Let's try that again. Manganese. Don't know what its charge is. P I do. phosphorus from the periodic table is 3 minus, comes from right here. Okay? So figure out the one whose charge you know. Okay? I have P 3 minus. How many of them do I have in the formula? Okay. 6 minus total in the formula. Manganese, again, since I only have one of them, manganese is going to take over all of that charge. This will be a 6 plus. I'll end up with manganese 6 phosphide. So sometimes doing it mathematically like that works well. Essentially all you're doing is dividing by the number of the other one. Right? I only have one of them there, so right? Knowing that you have to do that. Sometimes it's going to be helpful to do it sort of visually, understanding that you've got one manganese and 2 of these phosphide ions. So manganese, don't know what its charge is yet, but I've got a P3 minus and another P3 minus. Knowing that that group has to be neutral, the only thing we can do is to put a 6 plus in there to make it work out that way. Okay. For this last one, I'm going to show you a little trick here. Copper, still don't know. Okay. Transition metal, don't know it. We know oxide, though, 2 minus. Okay. What you can do is, if the ratio on one element there is the same as the charge on the other one, right? Here's 2 minus on the O that we know. If that's the same as the ratio number on the other, that means that the two numbers just got switched. Okay? So that's easy. Okay? That does not always work, though. Look at this. P was the element, the charge that we knew, okay? And there were no 3's over here. Okay? So in that case, it's easier to say P is 3 minus. I have 2 of them in the formula. So that means my other one has to be 6 plus, has to be twice that. Okay? But in some cases, right, the reason these ones don't match up is because 3 to 6 is reduced to a 1 to 2 ratio, and that happens a lot. That happens about half the time. Okay? In cases where the ratio was the same, it did not get reduced, then those numbers just got switched around. Okay? So what's the name of this one? Going to be copper 3 side. Okay. So what I'd like you to do, see if you can, here, let's actually go back. Let's go back a couple of pages to, where is it? Here. Back a couple of pages to this one that had the types of binary compounds. Now we're going to compare fixed charge with variable charge. So we still have metal and nonmetal. Metal cation, nonmetal anion. Okay. The difference here is that instead of one of these fixed charge metals, we're going to have a variable charge. Okay. Most of which are in the transition, but not all. I'll show you those in a second. Okay. But plus a nonmetal. It's going to be the same kind of nonmetal that we were talking about before. The difference here is whether it was a fixed charge metal. Let's write that. Versus a variable charge metal. Okay? And the difference in the example would be something like iron 3 chloride. We need that Roman numeral we need that Roman numeral to indicate that we have a 3+ charge on the metal. Okay? So Roman numeral added to variable charge compounds, because if it's a variable charge metal, we have to say what the particular charge was. Okay? So fixed ionic versus variable ionic, the only difference between those is where the metal came from. Okay? So here on this page where we've got type, okay, these are all ionic. It's all metal and non-metal. So just write a F or a V in there. Okay? So I want you to see if you can fill these out. Okay? I want you to start with the type. Okay? Fixed versus variable, okay, just based on where the metal is. Write the ratio. Remember, the ratio just comes straight from the formula. Don't switch anything. If you're given the formula, that is the ratio. Okay? What gets switched is going from ratio to ion pair sometimes. Okay? Or if those two numbers do not just get switched, if the charge you know doesn't appear over there, you have to ask yourself, like we did up here. Okay? If the charge we know, 3- isn't sort of the other charge, the two didn't just get switched around, there was a reduction that happened in here. So what you have to do is say, okay, I got 3- on the one I know. I have 2 of them in the formula, so you can figure out the total minus charge, then figure out what the plus charge needs to be. Right? The total charge has to be the same for plus and minus. If you have just one of them, that's going to take the total charge. If you have 2 of them, you're going to split that total charge over them, and so on. Okay? So I want you to see if you can fill those out. Okay? Again, I will not go through these right now. If you want to check your work, go into the completed notes in D2L, in content area. I'll put completed notes. What I will say, one more thing before we end this video here, is let's make perfectly specific which metals are fixed charge, which metals are variable charge, and we'll sort of have the last word on that now. So the fixed charge metals that we already talked about, okay, and we've got this periodic table right here that you can draw on, okay. These ones were plus, you can go all the way down. These ones were 2+. You can go all the way down. Okay, so that was 1A and 2A. So let's write those up here. 1A was plus, 2A, 2+. Okay. We also had aluminum and gallium, which are both 3+. Okay. Let's write those. Al 3+, Ga 3+. Okay. And now I'm going to add on 2 more metals that have fixed charge. Turns out zinc, even though it's a transition metal, is fixed at 2+. Silver is fixed at 1+. Okay. So what I'm actually going to do here, I'm going to draw a big box around all these ones that are fixed. Over here. Okay. And then also over here. Three plus, 2+, 1+. Okay. Those are the only metals that are fixed charge. Those ones and those ones. Okay. I better write zinc 2+ and silver plus up here. Okay. So, in other words, if your ionic compound has any of these metals, your name will have no Roman numeral because we don't need it. Right? For instance, if we had ZnCl2, that's just called zinc chloride. even though it has Zn2 plus and Cl minus ions, even though that's a transition metal, because that is fixed at 2 plus, there's no need for a Roman numeral. So don't call it zinc 2 chloride, just call it zinc chloride. Okay? All of the non-metal charges are fixed as well. 1 minus, 2 minus, 3 minus. So it doesn't hurt to write those on there, although that's not the difference between fixed and variable. Okay? The difference is where the metal comes from. So if these are the fixed charge metals, the variable charge metals are all the other metals. Okay? So all of the other transition metals, other than the ones that we showed up here, but all the other transition metals and the inner transition metals okay. So all of these in through here are variable, as well as these main group metals in here, tin and lead and bismuth and so on. Okay? So inner transition, all of these are variable. Okay? So all through here, all through here. Okay? Those are all the variable charge metals. So as well, the other transition metals, not zinc and silver, okay, but all these other ones, inner transition, as well as those main group on the lower main group metals on the right. Just say below the staircase. Okay. Although not. Aluminum and gallium. Okay? So variable charge metals, for those we need the Roman numeral. For the charge. Right? Or the plus charge. That's actually right. Because they're all going to be positive because they're metals. Okay? But if you encounter any of those variable charge metals, any of these, all through here, okay, those need the Roman numeral. So practice that a bit more. We'll be doing plenty of practicing in this in our next class. We'll be working in groups, practicing, making sure that we're getting all of our naming straight. Okay, that's where we're going to stop here. We'll pick up next week with the rest of Chapter 5.